Okay, so let's go ahead and get started. Joe asked me to come in and give a lecture on, or just a discussion on data science. So I work as a data scientist in Joe's founded company, Trifacta, currently. And I've worked in a data science role in a number of other places before that. And what I want to basically cover today is a bit of kind of what I do, some of the projects I work on. In the event that you're interested in this kind of work, I'll try to give you a little bit of kind of where the focus is, what the sort of nitty-gritty is, stuff like that. I'll try to end a little bit early so we have time for plenty of Q&A in case you have questions. And I can stay after class a little bit if you have other questions that are more oriented to one-on-one time. So, like I said, I work with Joe at Trifacta currently. Before that, I was a data scientist on the core data science team at Facebook, which up until recently was part of the engineering org there and has since moved out into what they call growth and analytics. Before that, I ran a team at RGA that did a mix of sort of data science and advanced prototyping. And then before that, I was a research scientist at Intel. And then a research scientist at Yahoo. And then before that, I was a grad student here at UC Berkeley in the CS department. I worked with John Canny. I didn't actually work with Joe while I was here as a grad student. But there you go. All right, so just kind of a quick agenda. I want to cover mostly projects, so I'll kind of take a project from each of the places I've worked and talk through kind of what I was working on, what was hard, what was challenging, what was interesting. Give you guys a bit of theory, not that data science is hugely well defined, but I'll give you a bit of theory, at least from my perspective, on what data science has to offer from a value standpoint. And then some of the practicalities of doing that work, and then we can end with some Q&A. So some projects. So this is my dissertation research from Berkeley, and this is a complete mess. The design was really bad. But what it was an attempt to semi-automatically organize information for people who spend a lot of time working with information. So not unlike you guys as students, you're reading lots of stuff, you're writing lots of stuff, you're writing code, you're organizing that stuff in folders, you're writing papers, you're sending emails, you're talking to people. All these interactions are shaping how you understand the things you're doing. So maybe that's class projects, maybe it's a term project, maybe it's an internship you're working on. And what we tried to do in this research was basically monitor all your interactions with these various pieces of information or people, and then organize it into hopefully meaningful groups. So yeah, the goal was at the end of the day to support information workers working on this stuff. And the idea was if we could do some of this organization for them, there'd be lots of benefits. So many people who get deeply involved in dealing with lots of documents find at some point that whatever organization they started out with is outdated. Things are never where they need them to be. And what we were hoping to build was a system that kind of evolved with people over time. So as your project took a new direction, new documents became relevant, new people became relevant, all this stuff would sort of shift dynamically along with your changes in workflow. So to give you a sense of the kind of data we were dealing with in this project, this is sort of a kind of a cartoon of what we were doing, but sort of documents and tools or sort of run and used or interacted with over time, and what we were doing was basically compiling that down into sort of time segments. So generally speaking, we were looking at multi-minute time segments. This says 0 to 30. I think actually we were doing stuff, we're on the order of like 5 minutes. But what we were doing then is just looking at, which tools were open, which applications were open, which documents were open, which windows were you switching between, who were you emailing with, these kinds of things. And then compressing that down into basically a large numeric file where each row corresponded to a chunk of time, each column corresponded to a different piece of information, different person, different thing you were interacting with. And then we were going to look at that essentially giant time series and hope to tease apart groupings of the columns, groupings of the pieces of information that you worked with. So if you guys have had some AI classes or something like that, you'll recognize that the matrix that's being built up here looks a lot like kind of standard bag of words. type representation, where each row is a document, each column is a word, and now you're counting the occurrences within that document, right? So we actually use that very explicitly in the research to basically say all the kind of topic clustering work that's gone on that deals with words relative to documents, we can bring that to bear here and look for similar kind of topical patterns, but now spread out over time of how people were working with information. So some of the challenges that we dealt with when we worked on this project, and I'll kind of come back to these different terms around challenges a few times as we go through it. But scope, for me, really means what is the data set supposed to cover? So in this case, the ideal situation would be that we gather a data set that covers every piece of information that person interacted with for the duration of the study or the duration of the time we were trying to support them with the tool. Now, the reality is what we could easily instrument was what they were doing on their computers, but as you guys know, you're in lectures, you're talking to people, you're having brainstorms outside, you're just thinking stuff up. That's not going to be captured by a system like this, right? So we have an inherent scope challenge in terms of doing this, which manifests itself really as we don't see a lot of the important information relative to the various projects or activities that you're working on. So we have a huge missing data problem, and we have to find a way kind of around that. And that's where this project went from being, hopefully, initially kind of an unsupervised attempt to find these kind of activities or clusters, and became semi-supervised. So now we gave people, through this interface, the ability to explicitly add new documents in that maybe we hadn't been tracking because they were using them before the study started, the ability to go ahead and edit, reorganize these groups. And so as the user was then providing guidance into the kind of groupings that were appropriate, that was getting built into the algorithms that were doing the clustering going forward. So another challenge was granularity, right? And this has to do with what is your data set fundamentally representing? So I said, you can look at that as sort of a document term matrix where rows are documents and columns are terms and you have counts. So in this case, our columns were mostly documents, and it was basically the amount of time you were interacting with that document. But there were also tools, so things like Firefox or Word, Adobe Acrobat. And we got to the level where we actually started mixing granularity. So for documents, because this was so focused on information, we actually would go in and rip the words out of a lot of the things that you were doing. So if you opened up a PDF, we could go and offline parse out the words and add those in as things to work with. So now we have a document term matrix where the terms are containers of words as well as words themselves. So now you have a funny granularity problem where you're trying to find patterns essentially across things that are ontologically different. And this is where we ran into some interesting challenges from an algorithm standpoint of kind of how you bias weightings from one to the other. So if terms, like literally the word shows up in multiple documents, is that a strong indicator that you want to group those things together or not? So you start to run into a lot of the same kind of problems that generally unsupervised topic modeling handles. And then there's measurement bias. So what I pointed out earlier was we were measuring basically the amount of time within a time bucket, so let's say a 5-minute time bucket that a certain document was interacted with. But a more realistic representation of what we would like to know is how important is that document to you. So we're using time of interaction as a proxy for relevance or importance. But I think you can easily think through lots of examples where that's not the case. So your project takes a big pivot. You spent a lot of time looking at a document only to realize maybe 10 hours into working with it that it's not really relevant for what you're doing, and you kind of drop it on the floor. But now I have 10 hours of interaction history that are going to come with the data set that I'm working with. Somehow you need to discount that or understand that that's not as relevant as perhaps something new that has much less time associated with it. And these kind of measurement issues in terms of the data set that you're working with to drive the patterns that you're finding, this is like part and parcel data science, where you spend a lot of time thinking about how the measurements that you're dealing with are or are not representative of the thing you're actually trying to study. Okay, so fast forwarding a little bit, this is a project that I worked on at Yahoo. So at the time, Yahoo had bought Flickr maybe about a year or two earlier, and this is right around the time that Flickr started frontline supporting geotagged images. So this is going back a while now. But it was very early in those days, right? So most people were still uploading images that they had taken on, point-and-click cameras that are 3 or 5 years older than that. No geotags, nothing like that, right? But a lot of people were starting to upload images from cell phones that did have GPS coordinates with them. And what we were working on was if you took the photo with now GPS coordinates and a timestamp associated with it, and then all the Flickr tags that people had attached to that photo, could you infer the semantics of the tags using the geo and temporal data that came with the photo, right? So this is essentially a semantics game. You're trying to find something interesting in the tag space using photos as a way to associate information. And what you're looking at here are photos for a chunk of time that were tagged with Hardly Strictly Bluegrass. So if you guys are familiar, it's a concert that runs every year. And so you can see this is a timeline on the bottom. There's a lot of very strong temporal concentration around the days of the concert. And then geographically, it's very much located in Golden Gate Park, which is where the concert takes place, right? So essentially, this now is a problem where what we're doing is a form of anomaly detection, right? So you say, Hardly Strictly Bluegrass as a tag associated with photos generally occurs this often in the world over these kinds of time scales. But then all of a sudden, there's this huge concentration over a couple of days and over a small region of space. So it was really the anomaly of the density of that occurrence that we were picking up on to say, all right, this is probably an event, given the concentration in time, and this is probably associated with a location, given the geographic density. So it's similar to the first project. We also had a scope problem here, where what you would ideally like to do is say, what I'm really trying to learn about is the tag Hardly Strictly Bluegrass. And now all the information I'm working with comes from geotagged photos in Flickr. And not just geotagged photos in Flickr. We had done some filtering to try to pick the ones that we were pretty certain had good GPS coordinates, good timestamps associated with it. So we'll get to that in a minute as well. But so that you're first of all, you're cutting off a huge swath of tagged photos in Flickr that don't have geotemporal tags to them. And you're throwing away all the other information you might use about Hardly Strictly Bluegrass. So we could have done web crawls. We could have talked to people, right? So now, again, you have this sort of scope problem where you're trying to infer semantics from, in some sense, a limited perspective on the data that you have to work with. And this is, again, very, very common problem in data science. Chances are, if you take on this kind of work, you're going to get landed with a data set, and someone's going to ask you to figure out what's in there. And it's all about figuring out essentially what it doesn't cover, because there will be a lot of stuff missing. So sample bias, this is a very common thing. In this case, because we were focused on geotagged photos in Flickr, that meant we were only taking the most recent stuff that was uploaded, and from people who tend to be adopters of newer technology, right? So those are the kinds of people that were going to do this, which meant they were more likely to go to certain kinds of events. They were more likely to take pictures in certain kinds of places, which meant if we were going to build an algorithm that could take geospatial data and generically infer place and event semantics, it was unclear whether we could actually make that extrapolation, given that we were biased on such a select group of people and the sort of measurements that came from them. And then measurement bias. So in this case, we were taking mostly geotagged photos from phones, but people could upload a photo to Flickr at the time and tag GPS coordinates on it. So there were other ways of attaching the geo information to a photo that we might use, but the vast majority came from phones. And if any of you have played around with lat-long coordinate stuff from phones, now this is going back a few years, it can be pretty terrible, and it can be pretty biased depending on the density of cell towers where you are, the density of buildings that might block GPS signals, how often your phone OS decides it's going to update its coordinates, what its default accuracy of GPS values are, all these sorts of things. So you run into stuff where BlackBerry was at the time pretty much unreliable, but Nokia phones were okay. And all that stuff has been sort of updated and revamped as the technology has gotten better. But from a data science standpoint, a lot of the geolocation information about people comes through phones, right? So you look at something like Foursquare or Facebook check-ins. So the location, the way they figure out where you are, help to provide suggestions to you, is the location signal that your phone provides. So there's a very strong kind of dependency on how good your phone's ability to measure these things are. But in many cases, it's unknown, and it's kind of shifting all the time underneath you. Okay, another project. This was at Intel. So I went to join a group called People and Practices Research, which was focused on studying how people use technology, right? So this is sort of a advanced market research branch of Intel that was supposed to figure out kind of in 5 or 10 years what were the big technology trends that might impact essentially silicon sales, but really the devices using silicon that people were going to use and how they were going to use them. And so when I showed up, the kinds of studies that we started doing were we would instrument people's laptops, phones, mobile devices of various kinds. So now you have like Ultra PCs kind of came out right around this time, or Ultra Mobile PCs, like the little tiny ones. And we would instrument these devices with essentially tracking software, right? So what applications were you using? When was it turned on? How often were you mousing versus keystroking? Now, we went through full IRB approval for all this stuff to bring people into studies. But what we would do is track essentially 6 weeks of data for most of these people across multiple devices, and then go in and interview them. And the reason why we would go in and interview them is we would produce these big posters of essentially the data that we collected, which applications you were using at which times of day, on which days of the study, how often you were mousing and clicking. We'd come in with these giant charts, and we'd sort of say, well, what were you really doing? Were you writing a letter to a friend? Were you doing work? Were you browsing the web? All these sorts of things. And really what was most important from Intel's perspective was not just exactly what were you doing on the device, but what was the context around you that might have dictated or influenced what you were doing. So this was the era kind of when smart TVs were really just starting to come out. And there were lots of questions of whether people would be looking at content on the device in their hand, whether that was a phone or a laptop, and whether that content would relate to the content on the TV. So if you go and look at how most people use devices, it's sitting on the couch in front of the TV. So now you have 2 streams of media, and the question is, are they correlated, right? And we're only now tracking one of these devices. So again, we have this kind of scope problem that I was telling you about. But what we want to know is that they're related. So that's what we were using the interviews to do, was to kind of triangulate around the data we had collected to understand that wider context that might have influenced it. This is a shot of, or a screenshot of part of a giant poster that we put together of cell phone data. So in addition to really focusing on individuals and trying to understand what each individual person was doing, we would step back and look at patterns across the entire study group to see, are we seeing like mobile gaming on cell phones, like seeing a big rise? Does it only happen at certain times of day? So this is a very common kind of data visualization called small multiples. Each day is a box. There's a lot of stuff going on in here. So there's stuff like how much of your usage happened at home versus away from home, of different application categories. So like social interaction stuff versus rich media, these kinds of things. And so we would spend a lot of time generating these visualizations and then working with many people to help interpret the patterns that we were seeing in that data. Yeah, this is just a screenshot of the kind of data we collect. Sorry, this is completely unreadable, but essentially every second we were collecting a pretty dense array of stuff that was going on. So some of it got very deep into what was happening with the hardware. So we wanted to know like the temperature of your CPU and how long it had been idle and these kinds of things. That obviously went to Intel's direct kind of manufacturing business. But what we then needed to do was abstract up a lot of levels to understand, like, well, what was the user really thinking about or doing or trying to do? So granularity, right? So yeah, back to that point of what we were collecting was kind of every second these very low-level event information. What we wanted to do is step back and say, hey, you just spent 30 minutes sending emails. Sending emails because it was part of your job, sending emails because you're catching up with friends. What we really wanted to understand is kind of that higher level interpretation of what was going on. And so we did have this granularity problem where we couldn't collect that data directly, but we needed to interpret from it that level of stuff. There was a huge sample bias in the study, so we had to recruit people into this, which means you're only going to get people who are willing to let you track what they do. people who are excited about getting paid $100 for 6 weeks of someone walking around kind of seeing what they do, this kind of stuff. And because of the nature of needing to go and interview people and collect this data, we were sort of limited to like a few thousand people in total over the whole course of this study. So it wasn't like we could go out like Facebook, let's say, and grab 1 billion users or 1 billion people and see what they're doing. So huge potential sample bias. And again, when you're trying to extrapolate out long-term cultural trends on technology use, that stuff matters a lot. And finally, interpretability, right? So this is the ability to take the data that we had, now these very fine-grained hardware, software events, and interpret that as sort of a wider indication of kind of human activities. And so data visualization actually became a very important vehicle for us to do this kind of work. It gave people who couldn't do the statistics, couldn't write the logging software, couldn't think about, let's say, all the math that would need to go into pulling a pattern out of this thing, but could visually look at something and say, there's something interesting that happened there. Oh, these 3 weeks looked really similar, but on this weekend, clearly something different happened. Let's make sure we understand what drove that. Okay. Next project is something that I worked on at RGA. So RGA is a creative technology agency, and they had been working at this point with Nike for probably 10 years and had been developing many generations of the Nike Plus experience. So up until the shoe that you see here, all that RGA was doing was simply the mobile app experience of kind of recording a run, and then the website experience that went with that, so to be able to look back over a history of your run, stuff like that. With this shoe, what Nike was doing was saying, hey, let's do more than just a pedometer. Let's add a bunch of different pressure sensors at different places on the foot, 3-axis accelerometer, gyroscope, a few different things to really get really granular on what the movement of the shoe was. And then let's build an experience out of that. And you can't really see it, but it was designed to be coupled with a smartphone, and in the smartphone you would download these packs. So there were packs for basketball as kind of like separate set of drills and stuff that you might do, and they had a specific basketball shoe for that. This is the training shoe, and the packs were coupled with kind of famous athletes. So like Manny Pacquiao came in and did a pack around like the kind of training he does to get ready for a fight. So be stuff like jump roping and push-ups and jogging and things like that. And so they would build these packs up, and what we could do then is take the sensor readings coming off of these shoes and basically score how well you were performing the exercises relative to what was specified in the pack. So you take something like a bunch of 3-axis accelerometer data, and you're trying to figure out, were you doing fast feet? Did you just do a burpee? Were you doing jumping jacks? If you were doing jumping jacks, were your legs really going in and out, or were you basically just hopping? So, we spent a lot of time basically doing signal detection on top of this stuff to assess how well you were performing these various activities. So challenges with this one. Certainly, you have the problem of measurement drift, right? So this is a new kind of sensing technology, something that sits in your shoe. Shoes can get pretty mucky over time, so there was unclear whether the pressure sensors would start to fail over time, in which case we would stop being able to detect events, or the accelerometer would get sort of wonked out and sort of stop reading on one axis or things like this. It was unclear how much of that would happen. Nike did a lot of work to kind of test the durability of these sensors, but it was still a big open problem when this product launched. And then you have sample bias. So the kind of people who are going to buy this are the kind of people who are generally going to be more active, who are willing to spend $300 on a pair of training shoes. They're going to perform exercises in a probably slightly different way than your general populace. So now your question is, if you're building a general classifier that's going to take these sensor readings and say, hey, you just did a burpee, how do you calibrate that, right? Do you calibrate it for the wider public? Do you calibrate it for who you think your purchase population is going to be? These were the kinds of questions that we were trying to solve as we were building the classifier for this stuff. And then you have algorithm complexity. So this is sort of a separate angle into a lot of this work. Most of it is about understanding the data and being able to leverage it. Algorithm complexity is really about maintainability. So now you've built this classifier, but now you want to add a new drill, or you want to add a different subpopulation into your data set. How easy is it for you to extend your classifier to incorporate this new stream of data, this new problem that you're dealing with. And this gets into very core kind of software engineering problem space where it's like, you almost always want to bias stuff that's easy to read, easy to maintain, easy to update over stuff that might be potentially slightly more accurate but impossible to change once you launch it. Okay, Facebook. So I left RGA, went to Facebook on the core data science team. What I worked on there was user profile information. So you're on Facebook. Facebook's going to ask you a question like this. Hey, where'd you go to college? And you're going to say, UC Berkeley. Some people go in there and they say, I went to Hogwarts, or screw you, Facebook, I'm not going to answer that question, or whatever they want to say, right? Now, Facebook leverages profile data to do a lot of things. A lot of it is directly user beneficial in the sense that based on who you said your friends are and what overlap you have in terms of profile information, they can do a better job of saying you might be interested in this content in your news feed more than that content. They can also do things like, hey, this person might be a friend of yours, you're not friends yet, so people you may know. I'm sure you're all familiar with these parts of Facebook. But that stuff all runs on the backbone of the additional information across friend links. And that information is, do you share profile information? Do you share interests? Do you share activities? These kinds of things. But the problem is when you get a lot of people who go in there and say they went to Hogwarts, that backbone starts to break down. So the problem that I worked on was how can we start to determine information that's reliable, as in information that we can use to drive these predictions, versus information we should probably toss out. And again, it gets used in a lot of different places, also gets used to drive ads, so there's that side of it. But it's an interesting problem in terms of how do you decide that Hogwarts is a real school or not. So all of you probably know that it's not a real school, but you get stuff like, Stanford University, comma, college, right? So at some point you start to ask the question, did they actually mean the Stanford that we all know, or were they kind of joking or putting something in that didn't make sense? Then you step back and you ask the question like, well, how is it that I would decide that, let's say, Hogwarts is a real school? So if you take all the schools that have, let's say, over 1 million people that say they've gone to them, and you look at, let's say, the social network around that, right? So take all the people who said they went to UC Berkeley. Let's look at all the friend links between those people. For a real university, generally speaking, you're going to see very high density and coverage in that friend graph. So there's probably at most like 2 complete connected components relative to a big university. Like almost everyone who's gone there is going to know someone who connects you to the whole group. You get to something like Hogwarts and you're going to see a whole bunch of pockets of friends that thought it was funny to put that on, but they're not connected to each other. So the density of the network graph is totally different. So that, along with a whole bunch of other statistics, are what you can use to sort of determine, hey, Hogwarts isn't probably a real school, so we should drop that out when we make recommendations on other things. So I'm getting ahead of myself a little bit, but yeah, so we have this sort of entity and friend graph, and we use basically the statistics that you can generate over that friend graph to do the prediction problem that we're dealing with. So scope is a huge problem here. Facebook is very good at dealing with stuff like Harvard, UC Berkeley, Stanford, Hogwarts. But for all the mainline schools that you can name, there's probably 1,000 other completely valid ones that are reasonably popular. Tens of thousands of people have said on Facebook that they have attended them. And then the next tier down, you have this huge long tail of stuff where 1,000 or fewer, sometimes down to like 10 people have said they've gone to this thing. So now you have very, very sparse statistics to deal with part of this distribution of schools that you need to come up with a decision on. And so this is where this problem becomes quite interesting, is how you sort of deal with coverage across or density of data across the entire problem space that you're looking at. In this case, all the places people said counts as a school. Essentially, this is a veracity problem. So this is kind of a very particular flavor of measurement bias where the measurement, in this case, people saying where they went to school, could be completely wrong. Now, one easy way to actually augment the prediction of all this stuff is to step back and say, well, hey, can I predict if someone's just generally a liar on Facebook? So someone who says they're 200 years old or female when they're male or is really into, let's say, basketball when they're not into basketball at all because they're trying to throw off the classifiers or this and that. And it turns out, actually, that you can do a pretty decent job predicting that general problem, and then you can leverage the results to bring to bear on specific veracity problems as well. And then, of course, you have sample bias. So certain kinds of people lie, and the kinds of people who think it's funny to lie on Facebook tend to be friends. I'm not saying either way whether it's good or not. I'm just saying it tends to come in groups like this, right? So your problem is now you're going to end up using a lot of network statistics to determine stuff. But if you get enough people together, so this is probably pretty common if you guys have had like an encryption class or security class, you get enough people together, you can pretty much break a lot of stuff, right? You get enough supposedly independent sources corroborating a piece of information, and most algorithms can't sort of work relative to that level of gaming. And the same thing holds on Facebook as well. Okay, so the present day. This is a screenshot of Trifacta's current product, which is a tool to help people wrangle data. My understanding from Joe is that you guys have worked with this. He made you guys wrangle some text or something like that early on. So this is probably slightly newer than the version you guys played with. But essentially the problem that we're dealing with here is we want to help people wrangle data easier and faster than they could otherwise do in other tools. So it's not necessarily a matter of giving them new functionality that they don't have elsewhere, but it's a matter of putting that functionality in their hand faster and quicker, right? And a lot of that happens through what the company calls predictive interaction, which is essentially a flavor of type ahead, right? Like you start to indicate that you want to do something by maybe touching a piece of data, and we should be able to look at that and say, hey, based on that thing you just touched, all the data around it, all the stuff you've done in the past, all the stuff that people in your company have done, we think you're probably actually trying to do this, right? And so that's what you're seeing at the top here is a bunch of suggestions on what you might be trying to do. So just zooming in on that a little bit. And, to varying levels of sophistication, right? We can do things like we know what common delimiters are. So if you highlight a delimiter, chances are you want to probably do something like throw it away or split on it, things like these kinds of things. But you can imagine this gets arbitrarily complex. So now you have a big, nasty, nested data set, and you're trying to extract a particular key. We haven't seen anyone try to do that before. Now we're in a problem where you have kind of the cold start problem, where you're going to try to predict something without any evidence that sort of predates it. And so we have to come up with kind of smart ways to bootstrap from good common knowledge, good common sense, but build algorithms that can handle new incoming streams of interaction as they happen. And so that's the big data science challenge that Trifacta has, is how to build sort of an evolving, ever-increasing expertise around how to give users suggestions to wrangle data. So scope problem, again, I kind of mentioned this. With a tool like this, you're going to constantly run into someone doing something that you've never seen before. So you have no data that represents or predates that experience. So how do you kind of bootstrap from what you have seen into new areas? And then granularity, right? So there are many number of things that we can bring to bear in the interface to make these predictions. So there's both what the user actually interacted with, but then there's all the metadata around the data set that we can see. There's all the similar data sets with similar columns of data that we've seen before. There's the kind of data sets that users interacted with in the past, all these sorts of things. And they live at sort of different ontological levels, right? So we have to find some way to blend all those different kind of features together to create good signal on what would be a good prediction for a user. And the biggest issue is access, actually. So Trifacta sells on-premise enterprise software, which means we tend to install our product into companies' internal Hadoop clusters. Generally, those things are firewalled off from the rest of the world, and there's no way to get in and out of them remotely, which means we don't get any real telemetry. It's very hard to get telemetry on what people are actually doing inside of that cluster with our product. So we have a problem of getting new data that we have various solutions for, but it's a challenge. It's an ongoing challenge. And this is something that's very, very common with data science. A lot of times, people will make requests like, oh, can we predict X, can we predict Y? And you might turn around and say, well, yeah, if we had data A, B, and C. You say, well, we can't get that, right? So how do you find proxies to work around access problems with data? So like healthcare is the most common one, where I think everyone agrees we could do a much better job of predicting illnesses, better treatments, all these sorts of things. But for better or worse, that data can't be shared across organizations, so it's very hard to even test out some of those theories. Okay, so just a quick review of different kinds of challenges that you will deal with if you choose to become a data scientist. So things like scope, does your data set cover all the things you want it to cover? So this is both an intra kind of question, which is to say, let's say I have a data set that covers human behavior. Does it cover all that person's behavior, or am I systematically missing certain things like when they eat, when they go to the bathroom, when they sleep, if you need that stuff? And then there's scope on this sort of kind of cross-person or kind of cross-entity level, which is, do I have the entire population? Do I have a representative sample of the entire population? Or did I get a sort of biased cut into that, right? Did I only get people who are under 30, people who live in Silicon Valley, these kinds of things? Granularity is really about understanding what your data set is supposed to represent. So the ideal case is you get a data set that's ontologically sort of uniform, right? It's all these event readings from a piece of silicon, the same type of event at the same time scale. It's equivalent across all the CPUs that you measured. The worst case is when you get stuff at different time scales. So maybe you get temperature on one, but on another one you only get like power consumption, which is a proxy for heat in many cases, but not perfect. So now you're going to try to do this match to get the granularity of data to link up between data sets so you can do a cross-data set analysis. You'll end up spending a lot of time trying to figure out these kinds of problems. And then, generally speaking, a lot of data is crap, right? So the data contained in it wasn't collected systematically, had strong biases in terms of measurement, had measurement drift where the value 5 means something different in the data 6 months ago than it does today. And that may be a measurement problem. It may also be a shift in the thing in which you're studying, right? So you can think about Yelp reviews, where the average Yelp rating, I think, has steadily increased from like 3 and change close to 4, right? So there's this natural inflation that happens on stuff like that where theoretically you need to back that out if you're going to look at whether a restaurant has actually gotten better over time or is just riding the natural trend of inflated scores. Sample bias we touched on. Veracity is really about whether you can trust certain information in your data set. So in the worst case, you have people that are intentionally putting bad data into your system. Access, of course, is a big problem, and interpretability. Okay, so shifting gears just a little bit, just to give you guys a bit of flavor on kind of some theory behind this stuff. How many of you are familiar with this? This is Peirce semiotics. You guys had a class on this? No. Okay, so this is kind of just classic semantics, very low-level stuff. The idea here is you have things in the world, you have objects, you have signs that people use to refer to or reference aspects of those objects, and then you have some interpretant, some person, some organization that's using that sign to refer to that object or that phenomenon, right? So generally speaking, all your data sets are going to be some form of encoded measurement of something in the world, right? So you now have GPS locations, which should refer to a place, but they may or may not, depending on measurement issues or encoding issues or this or that. And of course, all this is sort of relative to who's asking the question and why do they care, right? So certain levels of measurement bias are completely fine, depending on what you're trying to do. So the general process of doing data science is really to take this data set, which is this encoding of some phenomenon in the world, and go through this iterative cycle of interpreting that data to understand something in it, and then based on that new understanding, going back into that data set and looking for something else. So going back into that data set, I'm generally scoping or calling transformation because it often involves, reslicing your data. So you went from looking at stuff just in a pure timeline to saying, look, I only want to look at weekends. Or maybe saying, actually, what's interesting is geographic regions, not individuals, so I'm going to reaggregate all the data to look at regions and see if the pattern still holds there. So you go through this constant cycle of like, I think I understand what's going on here. I think I see something interesting. Let's think about that from a different angle, go back into the data set, take a different cut, take a different angle, augment it with new data, see if things still hold, right? So this is just kind of a classic scientific process. Have a hypothesis, test it out, figure out whether it holds or not. And when it comes to doing data science, at the end of the day, the value that you're going to add in most organizations is what you get out of data sets, what you can then say, hey, I learned this from the data set, or hey, I built an algorithm that will continually pump out this kind of stuff from that data set. And this is really somewhere in the spectrum of deduction to abduction, right? So deduction is literally I take what you gave me and I produce something that comes exactly from it. So kind of the classic stuff here is I took all the sales from Gap and I organized it by store, and then I organized it by region, and then maybe I organized it by clothing line. That's like deducing higher order information out of the existing data set. That has a lot of value. A lot of people need that. Generally speaking, as a data scientist, you're going to move up this chain, right? So at the end, abduction is really about inferring things about the world that aren't really in your data set. So now you're going to make statements about that object or that phenomenon based on the data you have about it, right? So I saw all these people say they went to Hogwarts. I looked at kind of how those people are connected. I'm going to assume that Hogwarts isn't a real school. So now I'm making an assumption about the existence of something called Hogwarts and some qualities about it. And that's where you start to add a lot of value as a data scientist, is in teasing out and sort of codifying these insights. Okay, practicalities. There are lots of people who work with data, not just data scientists, obviously, as you know. Just kind of thinking about this in terms of a circular spectrum here. You have data engineers who spend a lot of time thinking about how to maintain a data set, how to make it accessible, how to make it quick to work with, how to make sure that it's reliable and not breaking over time. You have data designers. So these are people who, like the New York Times say, that's making these really great data visualizations by sometimes working directly with data. Sometimes, obviously, they cross over into the journalism side where they spend a lot of time inferring a story out of a data set. And what that tends to involve is sort of picking a streamlined kind of sequence of insights from a data set and throwing the rest away, saying, like, this is what you should pay attention to in this sort of order. Tell a story about it, right? Somewhere out there are artists who kind of use data to just get inspired and do crazy things. And then, of course, you have your analysts. Generally speaking, now this is getting kind of overly stereotyped, but you see these types of motivations for working with data for these different types of roles. So you see journalists are really about telling compelling stories. So that's what they're going to try and find in a data set. Analysts are really about actionable insights. Scientists is really about knowledge creation. And this is why you spend so much time worrying about, can I trust the measurements in this data set? Do I trust the populational bias that's in this data set? These kinds of questions. Engineers, it's a manageable resource. It's got to be worked up. It's got to be maintained. It's got to be usable over time. Designers look at data generally as utility. It's sort of a constraint and an inspiration at the same time for them to do work. And artists, it's sort of pure inspiration. Okay, so coming back to this general cycle of interpretation and transformation, the reality of doing this work, and I think probably Joe would agree with this, is that you spend a lot of time transforming data. For every interpretation that you get, you probably spend 10x the amount of time working different angles into that data set to surface that insight, to justify that insight to yourself, to justify that insight to other people. And so it's sort of hugely important, sort of why trifacta exists, but it's hugely important to sort of recognize that in this work, the heavy lifting is really on the transformation side, but the value that you surface to the world is generally on the interpretation side. And to give you just a little bit more flavor on how that looks, it's really computer science skills, what you're learning here, that give you the ability to work with transformations in data sets, right? So it's coding ability, it's knowledge of how databases work, it's knowledge of how data gets stored and transferred, it's things like consistency and redundancy. Understanding how all those mechanisms are brought to bear to like generate a data set is important to your ability to actually transform and work with it. And then, of course, you have to have some domain expertise, right? So the data encodes something, whether that's how people are behaving in the world or how people want to rate a restaurant, or maybe let's say, think of Tesla, it's ratings on the functionings of that car. And you need to really understand why a certain level of vibration in a sensor in a car is maybe reasonable, maybe not reasonable. So having that domain expertise is important in understanding how to work with that data. And then finally, what ends up actually dictating a lot of the interpretation process is the mathematics and statistics of inferring or deducing or inducing out findings from a data set. So you have to have some understanding of how to do classification, how to do regressions, how to do general kind of higher order filtering on data sets. And that becomes your sort of tool chest of how you justify an insight that you surface out of a data set. So this is a pretty classic Venn diagram that a lot of people will draw for data science. In all the places that I've worked, it's been absolutely true. You have to have the computer science skills to work with the data set. The math and stat skills come with it just so you can justify the insights that you're pulling out. And the domain expertise is what allows you to sort of move forward, right? You have to be able to ask appropriate questions because there's way more questions than you're ever going to have time to answer. All right, that's all I had. So if people have questions, want to ask, that would be good. Yeah. Yeah, it's a good question. So it's hard to say on a single day, but I'll take like the average of a day over, let's say, a month. And you'll spend probably a couple of hours actually working with a data set, mostly writing transformations. So you're writing new scripts, new pipelines, SQL statements, whatever, to pull and cut out a new chunk of data. Spend maybe another hour actually figuring out what that new slice of data is telling you, how to interpret it. And then you'll actually spend the rest of the day going out and explaining to whoever you work for or work with what you found and why it's relevant. So it ends up being a very heavy communication role. Because there are, and generally speaking, there are a few other people who are going to just naturally trust the stuff you find, because it seems like black magic, you're able to tease this stuff out of a data set. So you spend a lot of time saying, well, if you do this, you can see it. If you do this, you can also see it. And if you do this, you can see it. And you hope that across all the different ways you're telling your story, you've managed to convince the people you work with that you actually know what you're talking about. Yeah, absolutely. Yeah, and so that's the average case. So you might go like months digging into a data set before you pull something out, and then you'll probably go on the road. So like the Intel case, we spent probably like 3 or 4 months collecting that data set and analyzing it, and then another like 2 or 3 months literally just going around giving presentations within Intel about what we'd found to just basically communicate the results out. So it'll come in sort of spurts, generally speaking. But yeah, I would say on a whole, that's the balance. Yeah.
Yeah. So like you're saying that like a lot of symptoms from like inside data, look at it and say, okay, this is does that sort of insight just come from the job, or you kind of sit down and have to look at it for enough time and kind of get to you, or is it something you learn? Like where does that come from?
Yeah, that's a good question. I mean, some of it will surface directly from like statistical tests that you know how to run. So someone might say something like, hey, sales are doing really good in Boston this year on like T-shirts. And you'll go in there and you'll look at it and you'll say, actually, you know what, if I normalize for the season and I normalize for the sale of cotton in general or for pants, it's not outperforming any other clothing line. Boston just happens to be buying a lot more clothes right now, right? So that like level of checking someone asking a question, that's like a pretty generic way that you'll get a lot of insights. It's sort of like, well, I'm not so sure. Let's ask the question relative to other peer groups. So relative to other similar things like pants versus shirts, right? And then there are things where you really do need to get very deep into the domain expertise where you have to say, okay, well, I know in Boston they have like 3 major sports teams. 2 of them did really well this year. A lot of people are buying that sports shirt, right? So I'm kind of pulling this example. This actually came up when we were working with Nike. So they, of course, really need to forecast how many T-shirts they need to print. And if it looks like, let's say, the Bruins are going to do really well, in hockey this year, then they need to go out and print a whole bunch of Bruins T-shirts so they have them to sell them. But if they screw up and print too many, of course, they're in big trouble. So these types of forecasting problems are like very common. And a lot of times the insight you bring to bear is, you come in and you say, like, well, did you account for seasonality? Did you account for the shift in the price of cotton? Did you account for, the depression, local depression, or the local inflation of commodity goods like milk? And so you'll get people who come in who bring like an economics background, so they'll come in and look at like the macroeconomics of the city to come up with some judgment. You'll have people who come in who really know like Nike's business, like, hey, I know we do really well when we sell green T-shirts versus blue. And so they'll have that level of insight that they can bring to bear. And generally, it's a collaborative thing, right? Like, lots of people will be involved. Yeah?
Why did you pick data science over like other like aspects of
It sort of just happened to me, honestly. So, I think my dissertation work, what really got me interested was was the problem of, can I find a pattern in your way of accessing information that's relevant to you and useful to you? So useful, I think, is probably the most important part, where it's like, yeah, I can come up with lots of different patterns, but I want one where you can look at it and immediately recognize what it is, and it shows you some stuff that would be otherwise hard for you to find, right? So documents show up in there that are relevant, that you were sort of like, oh yeah, that makes a lot of sense. I wouldn't have put that in there. Right? So I was looking for that level of insight, and that problem is more of understand kind of what's going on with people. And so that drove me into Intel and the People and Practices group to sort of look at understanding people. Of course, there are huge, awesome technical problems that underlay all of that stuff. But for me, it was just really trying to figure out that highest order value add to users that kind of pulled me in. Yeah. Yeah. Sure. Yeah. So let me take kind of two examples. Well, maybe three. So Facebook obviously has very large data sets. They're a huge user of Hadoop technologies. Mostly they've branched and they have their kind of own custom flavor of it at this point. And it drives basically the vast majority of work on data at Facebook. So roughly speaking, you can think of Facebook as the sort of production tier that serves data to users as you hit facebook.com and gives you photos and newsfeed and all that sort of stuff. All that stuff is driven by relational databases that are, very low latency, high throughput kind of systems to serve experience. But every hour, every day, all the data in those systems gets flushed out and dumped into Hadoop, and all the big heavy lifting prediction algorithms will end up actually running in Hadoop. So let's say every day I get a dump of every piece of content that every user on Facebook liked that day, and I might go through and analyze that data set to try and figure out, hey, actually, baby pictures are up. It's awesome. We should be pushing those up in Newsfeed. So that level of analysis can't be done in real time, requires Hadoop to do that scale of computation. So that happens in Hadoop. What will end up happening is you'll do all that analysis and then stage a table that says, hey, of the 10,000 kinds of content that we have, here's the ranking of how hot they are right now. And then that will get pushed back into the production tier that will absorb it to kind of rejigger how stuff runs. So I'm generalizing. I don't know. Newsfeed is far more complicated than that. But generally speaking, that's the flow. We pull data out of the front end into Hadoop, which is our back-end processing engine, and then stage results back in the front end to drive experience. And so, yeah, I spent a ton of time working in Hadoop. It's a skill set that certainly if you go to a place like LinkedIn, Facebook, Google, you'll end up dealing with kind of MapReduce and all the new flavors of in-memory stuff. So Spark and these guys all have in-house stuff that does similar things. So because Facebook does so much graph processing, they actually open source a system called Giraffe, which can do a trillion edges between a few billion nodes in memory in real time, or not in real time, but can process that stuff in a very efficient way. So they built custom systems to do the kind of computation that they need to do. Spark and its flavors, I think, are an attempt to build a generic in-memory solution for general MapReduce workflows. I think, generally speaking, in-memory is going to be much faster, so I think a lot of workloads are going to shift that way. But for certain things, MapReduce is really just the only way to deal with the scale, or you have to come up with something like Giraffe, which is super customized for graph computation, let's say, because those are the kind of algorithms you need to run. Trifacta built its product to run on top of Hadoop. So the value proposition was, hey, lots of people want to start working with bigger data sets. The biggest potential user base for that is all the analysts who are today doing stuff in Excel and Access and direct manipulation tools, but those don't scale to big data, right? So if you threw a big data set at that person that won't fit on their laptop, they're basically going to fall down with the tools that they have. So let's give them a tool that is pretty fluid and easy to use, but then can turn around and run in an environment that can handle large data sets. So that was kind of the inception of how Trifacta got built on Hadoop. I think if I were to give my independent of Trifacta kind of opinion on where that's headed, I would say there's going to be a huge kind of middle-sized to small-sized data set workflow that will go on for another 20 to 30 years. You look at let's say, like Chipotle, right? Chipotle has a lot of stores. They obviously do a lot of sales. But if you step back and say, look, I want to do analysis on like the commodities that drive Chipotle, that's a fairly small data set that you need to work with. Maybe let's say you have commodity prices on beans, rice, cilantro, chicken going back for like 10 years, and you're going to use that to forecast costs for them going forward. But so let's say you have 10 data points per day for 100 things. That's a pretty small data set. Chances are you can do that in Excel. So there's a lot of analysis cases where small data is completely sufficient for the use case. So I think that use case will stick around. But Internet of Things, the fact that everything is now digitized, we sort of log everything that happens in the digital world means big data workloads are going to come for sure. But I think they'll be concentrated in places that really need to process that, places that are driving like big digital experiences like Facebook and Google and YouTube and stuff like that. Yeah. Yeah, let's see. There's a few different paths that I've seen work out pretty well for people. So having a background CS is a huge win. What will come with that is general good math and stat skills, just because you can think sort of quantitatively very easily. Of course, getting more background in that's going to also help. So take 2 or 3 courses in that. If you can walk out of your undergrad degree with like a CS background and a math stats background, now you're in a pretty good place to say, hey, look, give me like an entry-level job where what I'm going to build on the job is that domain expertise. Now, you could kind of go the other route, which is go back to school and go, let's say, I'm going to go get a master's degree in chemistry because I'm going to do data science and pharmaceuticals, and I need a chemistry domain expertise to do that well. Or you can look at something like finance. So finance has had essentially data scientists now for like 30 years. The domain expertise that they had is financial markets. And a lot of times they would take math PhDs or math undergrads or CS or physics undergrads and say, hey, go take your CFA, right, which is basically build up general financial knowledge of how financial instruments work so you can model how these things are going to play out. And so that, I think, I guess I would say, generally speaking, domain expertise you can pick up on the job. Or if you happen to have something that you're really passionate about, of course, you probably already know a lot about it and you're kind of ready to go. The harder thing to pick up is the CS skills I've seen and the math and stat skills for most people. And so, just having that from an academic background is a huge win. But generally speaking, like data science is so new that there's not like a way to do it or a profile to have to get jobs. And I've seen actually, like Facebook is a great example where people are really interested in it, will come in as a software engineer, and a year or so into being a software engineer will flip over and become a data scientist. So that I've seen, is at least in Silicon Valley, the Bay Area, that's a really common trajectory, is start out in software engineering and move into data science. Yeah?
In your role as a data scientist, how often do you get the opportunity to create your own data sets through interventions with users, do A/B testing, that kind of stuff?
So at Facebook, that was like constant, right? I mean, there was the snafu probably like a year ago now where they were tweaking the emotional valence in people's news feeds. But for that one study that became public, there were hundreds of others run like literally at the same time doing not that necessarily, but similar other interventions to understand what the impact was. So it really depends on your environment where you are. Obviously, the big digital experience houses can do this stuff at scale very quickly. So they can get a statistically significant result on a small change in an interaction or an interface in a matter of minutes, oftentimes. And so they have huge infrastructures to roll these kinds of tests out and gather the results very quickly. That was actually, so the core data science team at Facebook, I would say 75% of the team worked on the experimentation infrastructure of Facebook. So what makes it challenging is you might think of something like Google, where you can, for the most part, do a straight A/B test. Like I can literally say, hey, if I change this from this blue to this blue, I can just literally grab a random sample of people who show up to the site, show them one or the other, and measure the impact, right? Now you do something like Facebook, and you say, I'm going to tweak something in Newsfeed. Well, that tweak in newsfeed is actually highly dependent on who that person's friends are, how active that person's friends are, how often that person shows up. So now if you just take a straight randomized study, you might end up putting two friends on both sides of a study right next to one another, right? Like, that's probably a pretty rare occurrence. But the network effects are so significant that you can't just take a true random sample of users and get meaningful results. So they needed a whole new infrastructure to basically set up study, like test experimentation groups. And then you run into stuff where like 8 different parts of the company are all tweaking parts of newsfeed, and you can't let those experiments hit each other, which means users can only be in one at any one time. So there was, again, like another huge infrastructure that went in to say, okay, this user's in this study for the next like 3 months, so they can't be pulled into other ones on these areas, these kinds of things. So, I mean, data science spends a lot of time both helping engineers build out that infrastructure, but making sure that, again, this gets back to like measurement bias and scope and all these sorts of other things, that the statistics that you get out of those studies are usable, right? That they're predictive of what the actual impact would be if you rolled it out to the whole user group. At Trifacta, because of the access issue that I pointed out, we don't have like a great mechanism to roll out new studies. And because we're on-premise release software, you know, we release every month, but we got to then get customers to upgrade in this. So it's not like we can make small tweaks kind of constantly and see what happens. So it really depends on your environment. But there's a huge value to being able to run those experiments on a regular basis, for sure. Anything else? No? Well, I don't know what the usual protocol is, but I guess we're at 3:30 anyway, so there you go. If you have other questions, feel free to reach out.